Good morning and welcome to the OActive Workshop on Personalized Predictive Models. I am Ioana Katsavou, the Dissemination Manager of AXIA Innovation.
We are happy to be organizing this event in the framework of the OActive project. OActive is a Horizon 2020 project on advanced personalized multi-scale computer models preventing osteoarthritis. Before we start, I wanted to go quickly through the agenda. We are happy to have with us Mr. Tobias Wiesenthal, the head of e-health, well-being and aging sector of the European Commission, who will give a short welcome to our workshop. Then the OActive project coordinator will also have the chance to analyze the OActive concept, and then the exploitation strategy for the OActive results will be presented. Followingly, we will have a closer look at some of the OActive outcomes, focusing on biomechanical predictive models for osteoarthritis management and augmented reality interventions. Then representatives from similar EU-funded projects, namely SILICOFCM, Precise for Q, EU stands for PM, backup, InSilc and Carbon will present their work in the area of personalized and predictive medicine. So at this point, I would like to highlight some organizational points. As you all know, the session is being recorded. Dissemination material will be developed after the workshop and will be available through the official OActive website. All participants should mute their microphones. We are not presenting. The presenters can switch on their cameras when they present, and we will have a group photo after the OActive presentations for dissemination purposes. If you have questions, please ask them through the chat by stating your name, your position or affiliation, and then the presentation title you refer to when you submit a question. And after the workshop, an evaluation form will be sent to collect information on your opinion on the workshop and also on the OActive concept and the impact that personalized medicine can make to healthcare. With this being said, I would like to warmly welcome Mr. Tobias Wiesenthal to give an introductory speech. Mr. Wiesenthal, it's an honor to have you with us.
Good morning, everyone. First of all, thank you very much for the kind invitation. And it's a pleasure to be here. As I said, my name is Tobias Wiesenthal. I'm head of sector for research in the unit e-health, well-being and aging at the European Commission's Director General implementing the digital agenda, so DG Connect. And on behalf of the European Commission, I would like to welcome you all very much to this workshop. And we're really delighted to see this workshop taking place for a number of reasons. First, of course, it is really a pleasure to see what the OActive project has achieved over the duration that now very soon comes to an end. I mean, you're going to see this in much more details in the first presentation, so there's no need to go in detail, but OActive really has managed to provide very important results on the development of in silico solutions for the management of osteoarthritis patients, personalized models, etc. And you have gone the extra step also to create a higher buy-in from patients by using tools like virtual reality. Secondly, we are convinced that important research results need to be used and being made use of by other projects and later on by society, instead of reinventing the wheel every time again. So in this context, it is very reassuring to see that you have managed to bring together very relevant projects, that you have managed to bring together the ecosystem of EU-funded research, and we very much welcome this exchange and are looking forward to this workshop also to enhance our common knowledge base. So thirdly, to talk a little bit more about visions, if you allow. I think we are all aware of the benefits that digital tools and big data and the enabling framework that we see in high-performance computer can bring in terms of personalized medicine. So if you allow, I'd just like to share a long-term vision of the contributions that a human digital twin can bring to healthcare. So we understand a human digital twin as a virtual, multi-scale and multi-time representation of an individual's body in all its complexity, describing the physiological and pathological state, a concept that brings together all the health data sources, from health records to imaging data, but also up-to-date data from wearables or Internet of Things, and combines this with different modeling and simulation approaches, and also makes use of high-performance computing, then you can say that such concept will revolutionize, will very much foster personalized medicine throughout the entire pathway, from targeted prevention, from faster diagnosis, prognostic assessment, but also, of course, tailored treatment and the development of tailor-made biomedical products. At the same time, this concept empowers patients to take care of their own individual health and also supports self-management, for example, of chronic conditions. And it will support drug development. So personalized predictive models like the ones that you have developed and that other projects have developed that are presenting today are a key component in this concept. But I believe the challenge now lies in linking and integrating different models, in bringing together different data, and in particular also to pool the knowledge. And again, from this perspective, we are very happy to see that this workshop has succeeded in bringing together a large number of very relevant projects on personalized computational models, but also on in silico trials. You altogether cover a very broad range of approaches and disciplines and diseases, from osteoarthritis to cardiovascular system, from tuberculosis to mental health, cancer and back pain, to just name a few of those. Moreover, as we all know, the semantics and interoperability and underpinning standards are key for talking to each other in technical terms. And at the same time, supporting the development of skills and in general fostering the ecosystem are important ingredients. And in today's agenda also, you have managed to include these aspects by 2 presentations. So with this in mind, I wish all of us a very constructive and fruitful workshop today. I would like to thank you very much, and back to you again. Thank you.
Thank you very much. Now I would like to invite Professor Kyriakos from University of Nicosia, the OActive project coordinator, to take the floor and present in brief the OActive concept, followed by Ioana Baruni, the innovation manager of the project, giving an overview of the exploitation opportunities.
Thank you, Anna. I will just share my screen for a second. Thank you. Okay, so I would like, first of all, to thank Mrs. Wiesenthal for accepting the invitation, as well as the other colleagues from the other EU-funded projects that accepted our invitation to be here with us today. I will give you a brief overview of the OActive project, our vision, our goal as we started this project, and then I will pass the floor to my colleague Ioana Baruni for the exploitation strategy. Now, our project is titled Advanced Personalized Multi-Scale Computer Models Preventing Osteoarthritis. And I will start by briefly describing what osteoarthritis is. For the people who are not familiar, it's a degenerative disease of the joints and most common form of arthritis that is causing pain and mobility limitation. It's quite complex disease in regards to biochemical and biomechanical factors involved, but it's quite common. It's the most important cause of disability in elderly population. Up to 30% of people over the age of 65 are suffering from osteoarthritis. The knee is a commonly affected joint. There are a number of risk factors involved, like age, gender, hormonal status, BMI, family history, occupation, physical activity, any past history of injury to the knee, or even depression. Despite the fact that it's quite common disease, it's not easy to define, predict, or treat. Progression is purely understood, and that has resulted in a lack of prevention and treatment intervention. And here where OActive comes in, and what our goal was to actually perform a holistic multi-scale analysis by using combination of mechanistic computational models, simulations, and machine learning in osteoarthritis. We'll do that by actually integrating a number of patient-specific information, like biomarkers, environmental factors, behavioral and social risk factors into the hybrid model and creating one very large database, multi-parametric database, with the aim to generate robust predictors for new personalized intervention for better diagnosis, delaying the onset, and slowing down the progression of the disease. We'll do that through augmented reality personalized interventions that will allow the patients to have a more enjoyable treatment or rehabilitation. Of course, the system will be validated in vitro system, in patient population, and in large data registries. This was the vision of OActive. And who we are 13 partners from 7 different countries. We have 5 SMEs and 8 research institutes. The duration of the project was 36 months and a total of 5 million euros. Different levels, from tissue levels, fully body biomechanics measurements, organ levels, biochemical factors, behavioral and social factors. All of these go into the hybrid modeling approach, and the result will be to have personalized prediction and perform gait retraining to patients through augmented reality game. The system was validated, as I said, in clinical trials and data registries, and of course, the results will be disseminated and explored even further. Now, we have 3 cohorts from where we collected data for the OActive project. From Spain, Cyprus, and Greece. The patients have different characteristics. From Spain, we have young patients aiming at early detection of osteoarthritis. In Cyprus, we have elderly patients suffering from established osteoarthritis, and in Greece we have athletes with post-traumatic osteoarthritis. Of course, we utilize big data registry, as I said, from osteoarthritis initiatives with more than 5,000 patients, and the UK Biobank with more than 10,000 patients. Now, from our clinical studies, we collected informations like biomarkers known to be involved in bone and cartilage degradation, biomarkers known to be involved in inflammation, and we also search for novel biomarkers like microRNAs in urine and blood, and metagenomic analysis of the microbiome. We also collected social determinants like socioeconomic factors, environmental factors, lifestyle, occupation, physical activity, and many other parameters. All these were inputted to the hybrid model. In addition, we had some mechanistic model data, imaging data like MRI, X-ray techniques, gait analysis of patients, and again, all these entered the model. We also measured, have measurements from tissue level. We developed actually in vitro osteoarthritis models that are cultured under continuous flow in bioreactors, where we can actually apply certain pressures and measure some of the responses of this tissue, and compare them with the results that we actually got from the patient population. Okay, all this data, and as I said, we created a very large multi-parametric database, were inputted to the hybrid model to generalize, as I said, personalized predictors, and go into the intervention game that was developed by our partners, where we will actually have gait retraining in a real-time fashion. I will not go into the details of this data and the outcomes of the project, as my colleagues later on will discuss them in more detail. And with that brief introduction of the OActive vision, I would like to thank you and wish you to have a constructive workshop. And I will pass the floor to Ivan. Thank you.
Thank you very much. I would like now to ask Ioana Baruni. Ioana, are you in the line?
Yes, yes.
Great.
Hi to all. I'm Ioana Baruni, and I work for CETRI, which is an SME based in Cyprus. And for OActive, CETRI was leading the dissemination, exploitation, and communication parts. Of course, AXIA was also very much involved in these processes, and AXIA organized today's event. I will briefly present you how we approached exploitation within OActive and how we basically built the exploitation strategy. I'm gonna turn off the camera to share my screen because my network and laptop cannot handle multiple things at once. So give me a second. Can you see my screen?
Yes.
But is it in full mode?
Not yet.
Not yet.
Okay.
Yes.
That's great.
How can I minimize this one, like here? Okay. So in the context of Horizon 2020 project, to give you some background, when we refer to results, we mean any tangible or intangible project output, such as data, knowledge, and information, whatever their form or nature, and whether or not they can be protected. By exploitation, we mean the utilization of the results in further research activities, in standardization activities, or in developing, creating, and marketing a product, process, or service. So the exploitation can be not only commercial, but also societal, political, or for the improving of public knowledge and action. Therefore, there is a variety of exploitation routes available, like spin-offs, startups, developing and selling products and services, contribution to standards, policy recommendations, patents, PhD theses, expanded networks, etc. The selection of the most appropriate exploitation route depends on the nature of the result itself, the nature of the entity that produced the result, the commitment needed in terms of time, resources, even passion, the appetite for risk, and of course on the potential benefits in monetary or other form. The OActive exploitation strategy is split into two paths. The first path is the joint exploitation, where we seek to define a longer-term vision for the OActive integrated system, which partners can shape as they see fit. For the second path, the individual exploitation, we seek to enable each partner to take their project results and exploit them for their own ends. In order to facilitate the joint exploitation of the OActive integrated system, we employed certain business tools and methodologies such as market analysis, market positioning, Pastel analysis, etc. The idea was that we had to investigate the drivers and the challenges in OActive's macro environment, the OActive's inherent strengths and weaknesses, and overall the parameters of how and when to position OActive in the market for maximum success. For the individual exploitation, first of all, we provided support to project partners for them to identify their results and classify them into short or long-term exploitable results. Then we discussed the preferred protection routes and exploitation routes, either commercial or non-commercial. And finally, we guided them through the conduction of some preliminary analysis in the same way that we did for the OActive integrated system. Here you can see the market analysis we conducted for the OActive integrated system. So we have placed the OActive in the personalized medicine market, which is of course expected to grow significantly in the upcoming years. We looked for osteoarthritis personalized medicine solutions that are already in the market, and these are mostly artificial intelligence supported solutions in the field of musculoskeletal radiology. OActive's scope is a lot broader than that, and therefore it is safe to state that currently there is no direct competition in the market. Regarding the OActive's target markets, these are primarily medical service providers such as hospitals and clinics, and also technology providers such as biotechnology companies, diagnostic test producers, biobanks, etc. Moving on to market positioning, OActive's position and opportunity lies at the intersection of the competition's weaknesses, the customer needs, and the OActive's key strengths. The customer needs are today largely unmet, and osteoarthritis has a big impact not only on patients but also on the society as a whole. Regarding current treatment options for osteoarthritis, there are concerns on their efficacy and safety, especially on a long-term use. Also, they are palliative and reactive rather than coordinated, proactive, and preventive. The OActive, on the other hand, could shift the emphasis in osteoarthritis treatment from reaction to prevention, promote targeted therapy, and thus reduce trial and error prescribing, adverse drug reactions, high-risk invasive testing procedures, and surgeries. It could also increase patients' adherence to treatment and help control the overall cost of osteoarthritis treatment for the society and for the patients. Next, we conducted a pastel analysis which revealed the political, economic, social, technological, environmental, and legal trends that could have an impact on the future exploitation of the OActive integrated system. So let's touch upon a couple of them real quick. A major social trend is the aging population. In Europe, we have declining fertility rates combined with increasing life expectancy, meaning that solutions such as the OActive that help in preventing and better managing chronic diseases will inevitably be of high demand in the future. On the other hand, we have an emerging legal trend that relates to cybersecurity. So the majority of patient interactions within the healthcare system involve the use of medical equipment and devices, most of which are connected to some network. The growth of connectivity creates an ever-expanding attack surface for cyber terrorists. So there is lots of room for developing cyber defense policies and capabilities, and eventually even establishing a coherent and international cyberspace policy for all big data empowered solutions, such as the OActive, to be considered by the general public as trustworthy and safe to use. In this last slide, we list some of the commercial and the non-commercial exploitation routes that the OActive partners wish to engage with after the project ends. So indicatively, we have novel AR-supported gait retraining, not only for osteoarthritis, but also for other joint diseases. We have portable devices for gait analysis, new diagnostic tools like biosensors for other bone and cartilage diseases, expanded portfolios with new services for rehabilitation centers and hospitals, of course, several publications, agreed collaborations among partners to jointly participate in other research projects on chronic diseases, further research into the causes of the disease and the subsequent design of potential therapeutics. And lastly, we have new knowledge on the regulatory and ethical challenges in relation to cross-border scientific processing of healthcare data. So that was for me. Thank you for watching and thank you for being here. I tried to be real quick because I noticed that we are a bit over time. So Joanna, back to you.
Thank you, Joanna. Thank you both for your presentations. I would now like to give the floor to 3 more presenters from the OActive project. Professor Bill Balzopoulos, Professor Paolo Lisboa from Liverpool John Moores University, and Dr. Yorgos Germazis from University of Patras that will present the main outcomes of the OActive project.
Okay, thank you, Ioana. I hope you can see my screen.
Yes.
Thank you all very much for attending online this morning. My name is Bill Baltsopoulos. I work at Liverpool John Moores University, and together with Professor Paolo Lisboa, Dr. David Bridgman, and Professor Maganaris, we are working on two different aspects of the projects of the OActive project, namely the biomechanical multiscale modeling in our team in biomechanics, and Professor Lisboa's team in applied mathematics are working on the hypermodeling of the data. So I'll just try and go very quickly over some aspects, just to emphasize some of the aspects of osteoarthritis that Kyriakos explained. The problem that we start with is that the disease has no cure, so the treatment and the management of the disease relies on targeting the various risk factors that we know are involved in the onset and the progression of the degree of the disease. The problem is that all those factors that Kyriakos explained obviously are highly complex. They interact with one another in the human body. So what you end up with is high dimensional and heterogeneous data, making it difficult to come up with tools that will predict either the onset or how quickly the disease will progress, and therefore how you can manage it more effectively. So as Kyriakos explained, the main concept of osteoarthritis was that we will collect a large number of data from different domains, both biochemical, biomechanical, but also behavioral data, because all these factors interact in the life of a person to either lead or develop the disease or progress in at different rates with osteoarthritis. And through some complex analysis that a number of other partners and Professor Lisboa's team here have developed in analyzing the data that we collect, we hope that we can come up with some solutions or tools, if you like, that will help manage the disease in terms of identifying people at risk, but also having tools to be able to reduce the loading in the joints, which is one of the main drivers for the disease. Simply described, if you sort of take out all the complexity, because it is a complex process to try and analyze the data, a sort of a simplified, if you like, concept would be that you're trying to deal with the complexity in the risk factors that are involved with osteoarthritis to come up with some effective tools at the end. We, as Kyriakos explained, we collected a large number of data in 3 different centers, so I'm not going to spend a lot of time on this. That was quite a complex and difficult process. And if my computer unfreezes, the prediction tool in osteoarthritis are not new. There are several risk prediction tools that were developed in osteoarthritis. The idea is not novel. This kind of prediction tools based on the risk factors was developed mainly for cancer and cardiovascular disease. But there are several tools that have been developed over the years for osteoarthritis. Again, without going into a lot of the detail, most of these risk prediction tools, as you can see here at the end, rely on a very small subset of parameters and risk factors that we know are involved in osteoarthritis. So if you like, they are very selective in the type of factors that are targeting for prediction. Whereas, as I said, the the approach that we took is that since the disease is highly complex and individualized, we need to consider in detail a large number of factors. But the moment you try and do this, obviously you're faced with a number of complexities in how you handle that, the high dimension and the interaction of this large quantity of data. So the thing that I'm going to discuss today is mainly what we did in the computational modeling of osteoarthritis, and how Paolo is going to explain a little bit how we used, in our case at John Moore's, regression models to try and understand some of these complex relationships. In our work in Liverpool, the multi-scale modeling relates to looking at loading at the body level and then going all the way to the tissue level. So we developed biomechanical models that are personalized. That is to say, they can calculate loading in an individual by developing techniques that give us information about the loading in the knee joint. And this type of information in terms of the loading in the knee is one of the parameters, one of the risk factors, if you like, that is entered into the OActive database that is then exploited and analyzed with the multi-scale, with the hypermodeling. We developed a complex system. This is published, and what the system allows us to do is to analyze the movement of individuals, either gait, standing up, or going up and down stairs, and that allows us to calculate at an individual level for an individual based on the model of the musculoskeletal system, the loading experienced in the knee joint. So we're going from having imaging data for an individual, building up a knee joint model, and then combining that with the motion analysis data to predict what is the loading in the knee joint. So let's see if I can control the videos here. I hope you can see that basically once you do the modeling of an individual's knee, this finite element modeling allows you to then see the loading. And for example, the video seems to be a little bit slow, but basically if you have a healthy individual versus somebody with osteoarthritis, you're able to calculate the maximum load that is experienced in the knee joint in the particular individual. The numerical value of this is entered into the OActive database, and that's then where this information is exploited. So what we're contributing is personalized individual knee loading data that is then exploited as part of this modeling. So as I explained, we tried different types of models, both regression but also machine learning and deep learning models in exploiting or exploring rather the large data set that we have in OActive, but also, as Kyriakos explained, exploring other existing databases such as the Osteoarthritis Initiative, with a view of developing a prediction tool that will use a number of risk factors that we can measure in individuals and come up with a strategy, if you like, in terms of reducing certain factors that will then either slow down the onset or delay rather the onset, or slow down the progression of the disease. So we're looking at a hopefully useful clinical healthcare tool that can be used in clinical practice that will help a clinician deal with the complexity and multidimensionality of the risk factors involved in osteoarthritis. I'm sorry for the speed. I hope I've explained the concept, and hopefully Paolo can share his screen and explain some of the work that they've been doing in sort of trying to explore the information in that rich data set that we've been collecting.
Okay, I'm ready to share my screen. So if you can hear me?
Yes.
Okay, my name is Paolo Lisboa. As Bill mentioned, I'm going to talk about the regression analysis that we have done in relation to models for prevention and understanding of knee osteoarthritis. We have validated our results on the OActive data, but developed predictive models using one of the largest data sets available, which is the OAI data set, which, as you can see, is complex in its development and contains over 2,000 cases. In this context, we've explored a variety of models, both machine learning models such as CART, which is a rule extraction model, and neural networks, including deep learning neural networks, and logistic regression analysis. We found that because the data are so noisy, some of the statistical methods offer good predictive accuracy, as you can see from the area under the curve. I'm going to skip through the detail of the analysis on the OAI data and go straight into the validation. In the validation, we have used data from the next largest cohort available in the world that has been very carefully followed up. That is the multi-center osteoarthritis study dataset, most dataset. So we externally validated our models, having modeled data from the OAI. We predicted on this completely different dataset that we did not do any optimization on at all. We simply just predicted as an external validation, completely blinded, and we kept pretty much all of the accuracy, showing that our model has predictive value. Based on this, we have produced what's called a nomogram, and this is where the results for who is likely to have knee osteoarthritis at the baseline presentation, first presentation to the clinician. This is where the results become useful for other projects and for the public at large. The clinician, or in fact anybody, but in principle the clinician, will enter on the left the characteristics of an individual, their age, the BMI score, which is banded, the gender, certain baseline symptoms, including pain, difficulty getting upstairs, which relates to biomechanics, and stiffness parameters. And as a result of that, there will be a score that's derived. You will see some red dots. Those red dots indicate the parameters for this individual. Those red dots each have a score that projects onto the line at the top. Those scores are added up and they're compared against the threshold, which relates to the probability of developing knee osteoarthritis. And the threshold is the prevalence of knee osteoarthritis in the population that we studied. So values to the left indicate less than average, if you want, probability of having it, and the results to the right indicate more than average probability. And for this individual patient, which has got many protective factors, the probability of having knee osteoarthritis is low. However, you can see that if the BMI changes, right, then the score will change and this line will move towards the decision point for knee osteoarthritis. So this is a modifiable factor that can be, where the individual can be advised about the impact that change in their weight might have on their propensity to develop knee osteoarthritis. On top of that, we can see from the sheer size of these lines and where they are positioned in relation to the scores, how far and how much each of these parameters impacts on the diagnosis, and by exactly how much for that individual. So this provides the clinician with an explanation as to why the prediction for this individual is what it is. In addition to this, we did some deeper work. Some of that was to look at something which people still can't properly understand, namely that there are people radiologically identified knee osteoarthritis that have no pain, and those with pain and no KL or radiologically identified knee osteoarthritis. And if you compare the radiological index against the pain index, you see absolutely no correlation. However, when you do model data, you find that there is a correlation. You can see that there's a big group of green of people who have no pain and no radiological osteoarthritis over here, and a big group of red of people who have both, and there's a relatively minority of subjects that are where you have the contradictions, which indicates that there is a substantive physiological effect, which is then overlapped with some more subjective effects that mask it. So we have been able to start opening that box to see the relationships that may well exist between radiological KL and pain. Now, having discussed the propensity for having knee osteoarthritis at first presentation, we went beyond the scope of the timescale of the data, and we looked at survival modeling over 5 years. Again, we produced a longitudinal data model for the OAI data, and we identified the key parameters and also stratified the population and using rigorous statistical tests, and identified the population had 2 cohorts, a cohort that got higher survival, meaning a higher probability of remaining disease-free, that's the blue curve, and that's the probability of survival in this context of time to event data refers to being disease-free. And the red cohort has got a lower probability of remaining disease-free, so probability in this case about 50% of developing knee osteoarthritis in 1, 2, 3, 4 years. This is in days, definition of day being 365.25. These are the predictions and these are the observations, and we were able to also validate this for the most data set. Now, the most data set has certain artifacts, very little follow-up for the first few years, and the sampling rate is very small, very, very discrete, but you can see that our population predictions are very well stratified, and the observations are stratified but they do have significant confidence intervals because of the structure of the follow-up. Nevertheless, we do have clearly identified cohorts, and we produced also a nomogram, and this nomogram is now for the probability not of people presenting with knee osteoarthritis, but rather developing knee osteoarthritis in the next 5 years from the day of presentation. Again, the clinician, this is an app, and the clinicians can insert the details of the individual, and the scores for each symptom are present, added up, and they map onto an index here where there's a cut point that separates the low risk cohort from the high risk cohort. So for each individual, you know exactly how far that individual is from this cut point, whether the individual belongs to one cohort or the other, or is close to the boundary, and why that is. And we can also indicate to the individual that if the BMI were to change, then we would be able to change the overall score. And you can see here that the BMI has a very significant effect that changes the score from one cohort to the other. So this is how we intend to present the results of OActive for predictive modeling to contribute towards an understanding of the disease in terms of clinical factors and towards predictive approaches that can be used by other projects and by the public. We have validated all of these models on the OActive data itself, and that's as far as I can go. So I'll stop sharing. We also did some analysis on the biomechanical and other factors, particularly the biomarkers, and we have results on those. However, those results are for relatively small data sets, so they are more for research purposes, whereas these results are results that are potentially of clinical usefulness. And I don't think there's a time to discuss those in detail. So Joanna, back to you.
Thank you very much. I will now give the floor to Dr. Yorgos Yarmantzis. Yorgo?
Okay, I just unmuted. Let me share my screen. I hope you're watching my screen. Okay.
Yes.
Okay, nice. So, hi everyone. I'm Yorgos Yarmantzis. I'm a postdoctoral researcher working at the University of Patras and working for the OActive project. And I'm going to go briefly through the main outcomes of our work and what has been done for the OActive project. So in the following slides, I will briefly go through the basic concepts of guide training and present you the latest developments of the augmented reality, the AR or active guide training system, including the hardware and software elements. As we have already listened from the previous speakers, especially from Professor Boltzopoulos, mechanical forces acting on the knee joint are closely related to knee OA and local cartilage degeneration. The different non-invasive ways to reduce those forces have been proposed and used widely, such as braces or several guide modification strategies, all focusing on the medial part of the knee and the reduction of the knee medial joint torque. Some suggestions for guide modification include increasing the walking pace, walk with the toes rotated externally, the toe off, or walking with the torso bent sideways. However, all these guide modifications have been said to be uncomfortable and not sustainable in the long term. So the question remains how to change our guide to offload our knee structure and suggest an intervention for the knee OA patients. Also, is there a combination of those modifications which might have a positive result? So even if we find an optimal strategy, how we make this a sustainable one? In the OActive project, we believe this should be done through a software platform that gives continuous feedback, relies on professional supervision, be attractive to the users, and implement gamification elements to provide feedback to the patient in a seamless way. In principle, for this OActive approach to work, first we need calculation of knee forces in real time as a backend module. For that, we need both a motion capture system, it can be either market-based or IMV-based, and a rigorous musculoskeletal modeling system to provide important biomechanical metrics such as joint angles, muscle, and joint forces. Everything should be done in real time. The software and hardware requirements were investigated in order to develop the complete OActive guided training system. It was decided that the main core of our efforts would be the development of a real-time musculoskeletal analysis An outdoor solution based on IMUs and in-foot pressure sensors would also be explored. OpenSim was the main software platform that was used for that purpose. Regarding the hardware configuration needed, we decided to use Unity as the main game development software and use specific glasses for the AR implementation. The developed system includes the clinician-facing front ends. Here we will explore the functionalities of the clinician front end. Some key points of the interface include different areas of visualization options. In the main area, the clinician can choose to visualize the skeleton or part of it, the muscles, which are updated for every frame in terms of their parts and their activation levels. Also, the clinician can choose to show the ground reaction or joint forces, which are represented as straight lines, starting from the origin, whose length is proportional to the magnitude. In the ground, you can see indicator of guide-related parameters. The user can also choose to visualize or hide different muscles, forces, or bones. Also, the interface provides option to plot the different metrics, provided in real time. Here you can see how the knee forces acting on the right leg can be plotted. The user can select the color and change the label of each graph. Here you can see how, I think it froze. No, I hope not. It froze on my computer. Is the video running to you guys? Because I see that the video has frozen.
No, it's not running yours.
No, it's not running it. Oh, okay. Oh, maybe I'm mistakenly paused it. Okay. So you can see the forces acting on the ring. Now you can see the plot, and it runs real time. And then you can see the option to plot multiple parameters. Okay. So we will have plotted the knee force, the knee joint force, and you can also see the knee adduction moment, which is also relevant to the knee loading. And also, finally, the user can select which metric wants to see after making the plot. So also you can use some primitive indicators of selected metrics, such as bars or gauges here. There is also work in progress. We will implement a vibrotactile feedback as well to the patient through a wearable vest or belt. So let me, okay. So here we saw the front end as seen by the patient, either through screen or AR glasses. This work included the game development based on the updated OActive gamification approach. Decision has been made on basic gamification elements to be included in an exercise agnostic framework. That is, the game can be implemented in any exercise scenario. So simple visualization cues were integrated based on metrics set by the clinician. You can see here, okay? And now you can see, last in the next demo, we'll show how the prototype version of the OActive guide retraining system works in the case of an individual performing single leg hop, exploring both the clinician and the patient front ends that we've seen in the previous slides. I would like to point out that the selected exercise was intended, but it was intended to be walking, but it couldn't be done because there was no treadmill available in the motion lab that we were testing. So hence, we could not record walking continuously and give meaning to a guide retraining process. Okay, so let me start the video here. We begin with the clinician front end. Okay, first there is an observation stage where the clinician asks the person to perform the exercise habitually and decides on the range of the selected metric. The clinician chooses the jump height as a metric to be followed during performance. And now, I would like to check for example. There is option for video stream. On the other hand, the individual wearing the AR glasses can log in to the OActive system and navigate through oral commands. A welcome screen appears and the patient can sign in with individual credentials. When the clinician begins the session, the simpler and more intuitive patient interface appears. So you can see here in the video of the clinician presses the play button, and then you go again, you can see the patient, how it sees a simpler version. And then the observation stage, you have the optimization stage that guides the patient to achieve the desired jump height based on primitive visualization cues. You can see at the right lower corner how the patient sees and the clinician front end on the rest of the screen. The clinician can see both front ends and can check the progress of the individual while performing. Now the patient can see an avatar and different scores like session score that motivates the patient to improve with every session. Score combos that motivate the patient to be consistent throughout the session, and golden points that reward consistency throughout the entire rehabilitation process as they may accumulate over multiple sessions. At the end, the different scores gathered based on the performance are depicted and uploaded in the database along with other important variables and files. So we also invested our efforts also to develop the mobile solution with some remarkable results. As you can see in the video, we have managed to integrate the IMU and foot session signals with a real-time full schedule analysis module. A complete work on the OActive guidance training system has been recently published for further reference. Last, we're very proud that we're selected as finalists in the category Tech Society for the Innovation Radar Prize 2019 for this work in real-time school-schedule model simulation. Of course, our team have also contributed to other parts of the OActive project, such as the automated segmentation of knee MRI images and the overall subject-specific mechanistic modeling workflow. Thank you for your attention. I will be waiting for your questions at the end of the workshop.
Thank you, Yorgos. Thank you all.
Yes.
As Yorgos mentioned, you can write down your questions at the chat box, identifying the presentation title, and we will reply to them at the end of the presentation of the workshop. Having concluded with the OActive related presentations, we can switch on our cameras if you'd like and have a screenshot to use it for dissemination of this workshop. Great. So I would like to ask everyone to keep the timeline because we're a little back in time, but we will now proceed with our 6 cluster project presentations. And firstly, Professor Filipovic from BioIRC will present the SILICOFCM concept, the computational platform for in silico clinical trials of familial cardiomyopathies.
Okay, hello to everybody. I hope you can hear me and see me, right? And my screen,
Yes.
right?
Yes, although it is not in full mode.
Okay, it will be. Okay. Thank you. So, as I'm very glad that we have opportunity to today to present to each other our project. So I will present SILICOFCM. So it's actually in silico trials for cardiomyopathy disease, and actually we wanted in this project to combine all the specific patient features like of course pharmacological, clinical, genetic, imaging, patient-specific cellular aspects in order to first to understand cardiomyopathy as a disease, and of course try to make some kind of in silico clinical trial solution in order to reduce of course the real clinical trials and to understand and to predict this disease, and of course for drug treatment, very important how these diseases actually develop in the specific patients. So of course this is a multi-scale integrated multidisciplinary platform where we are using a different technology actually. Of course, one of the main components, data mining or risk stratification component. We are using bioinformatics tool with variant recovery, variant annotation, and of course, full 3D numerical modeling, finite element simulation with total heart and the very specific musical, this is the name of the software which we're using for micromechanical in sarcomere event, where exactly we're going on the cell level and try to make a connection between macro and micro simulation. So a number of partners are here. We have technical, clinical partners also from Europe, from US. We have also some partners and companies, and actually the point is to make very good impact. Of course, in order to reduce the human clinical trials, to be more effective, and to reduce animal testing, and to make some kind of platform for innovative medical product, setting the new standard, of course, to FDA, EMA, and for in silico trials, and of course to provide some kind of open access virtual patients database, and in order to provide for the maybe new biomedical product testing and etc. So this is just the main concept. So of course, all of these patient data are collected. Medical doctors are one of the main users of our platform, of course. Then we have pharmaceutical companies and of course academic researchers. So this is just a tools and their connection, starting for 3D image selection, segmentation tools, virtual population database, bioinformatics tools, virtual experiments database with real experiments, and of course a micromechanical model. And to make actually point as risk stratification tool and prediction cardiomyopathy disease progression with drug efficiency, which is very, of course, very important. In order to do this, we are also have a partner from Barcelona Supercomputer Center with the ELIA software and PAC software for the simulation of the total heart. This is just a presentation if just the medical doctors are users or pharmaceutical company are the users, and if researchers are the users in terms of exploitation of the project. Here we just presented some of the initial results with complex electrical field, electromechanical coupling for the parametric model of left ventricular, and also a real heart model with the two chambers, and of course left and right in different time steps and different resolution for simulation. This is realistic model electrical field and boundary conditions as presented here with orientation of each fibers on the top, and of course you can see how the fibers are geometrically distributed in the biventricular heart model with electromechanical coupling of the model. For parametric model, which we are using actually for echocardiography data, this is just the basic parameter, and we discuss a lot with clinicians how they can use it in everyday clinical practice. Of course, PV diagram is very important for the LV pressure and LV volume, and this is actually what they are doing today, and just some small simulation of the distribution of velocity and pressure in PV diagram. And for everyday clinical practice from echocardiography, we are building the system which can help them in order to understand each patient particularly, and of course try to understand the cardiomyopathy as a disease. In order to make a more realistic heart model, we need, of course, to use a large-scale system with the fibers, with direction, with the very specific material models, and of course, using calcium function and using very specific genetic data of the patients and specific boundary conditions for inlet, outlet, cross-section, mitral valve, and aortic valve, in order to simulate realistic 3D simulation in each patient what's going on and the current situation, and of course to predict in the follow-up and try to make validation of this simulation. Here is just a torso model with all the components with ECG, standard ECG, which is a very cheap, very useful tool for the initial cardiac current situation of the patient. And we also try to make inverse modeling in order to see where is the ischemia and where is the part of the heart tissue which is has some kind of fibrosis, and make this disease cardiomyopathy or hypertrophic or diluted cardiomyopathy progression. Body surface potential map with the heart activation model are using here. So we can see for the different time step in the one cycle, what's going on with the activation, which part of the heart is activated, and of course simulate on the torso what's going on and compare with real ECG in order to see the situation for these patients, and of course to compare with the measurements of the ECG. Of course, here is a complete electromechanical system which are using starting from the cell level, on the tissue level, and the macro level, what's going on in the measurements. Biomechanical, very complex system, and of course, three different area: blood flow, fluid mechanics, mechanical deformation, solid mechanics, electrical propagation, and different interaction between all of these three fields for the simulation. We are also using O'Hara-Rudy model, which is very new model for the simulation of electrical field. There are all the channels inside the heart and inside the cells, cardiomyocyte. So we use also different theoretical model and comparing with the experimental in order to simulate on the macro level. For the large scale simulation, this is just some example with the total heart with both left and right ventricula and atriums, and of course you can see very complex simulation streamlines here, what is going on, and our aim is for each patient to make this kind of simulation in order to predict the current stage and of course the follow-up for these particular patients during the therapy and of course during the disease progression. Some of the also solutions are presented here for no pericardial boundary conditions, or different segmentations resolution with the MRI or CT, and of course different phenotype for female and male patients, and distributions of the voltage time and during the each heart cycle. The main point, of course, for us is how to exploit these results, and we are talking a lot with pharmaceutical companies, and the main point is to make some kind of virtual drug testing on our platform, where from drug database the user can select some of the drug or combination of the drug, make some kind of internal calculation, drug protein interaction, and collected all the information, go to our SILICOFCM platform, make full 3D simulation, risk stratification with data mining, and make clinical decision or help clinician to do some clinical decision for the particular therapy of the patients or combination of the drug for this patient. Of course, some new drug can also be added here, but we have to know exactly the reaction of the drug on the micro level, on the cardiomyocyte level, and of course, some parameters we can also measure directly from the patients if we take some sample with a small device where we can measure deformation of the sarcomere or deformation of the cell level. This is a specific impact, so we have a number of the tools inside, and exploitation phase, of course, we are talking with different users from academic level, hospital level, and of course pharmaceutical level, and these tools we are in the last year of the project doing the validation of each tool separately, and of course integration of the tools. So from 3D segmentation, virtual experiment database, virtual population, data analytics tools, finite element simulation, bioinformatics, and musical micro level tools. So you can follow us on different, of course, social networking, Facebook, Twitter, LinkedIn, and of course our website and our YouTube channel. Thank you very much for your attention.
Thank you, Professor Filipovic, for the interesting presentation. Now we are moving to Precise4Q, precision medicine for stroke using hybrid, multi-level, and multi-timescale modeling, presented by Professor Sedersen from Linköping University.
Yes, so I'll start my video and I started sharing. Hopefully you can see it. Can you see now my presentation?
Yes.
Very good.
Thank you.
So, thank you for the invitation to this workshop. It's super interesting and aligns very much to what I will say and what we are doing in Precise4Q, which deals with predictive modeling, the type of modeling that you've seen already for other diseases, but now for stroke. And my name is Gunnar Cedersson. I'm at Linköping University. And we are developing this type of digital twin solutions. And this is also the basis for our spin-off company, where you see a little digital twin here of a cedar tree. And the name of the company is Sund, which is, means healthy. And it's part of my last name. However, I am not the coordinator of the network. That's Dietmar and their roles. So like many of you, we have, as one part, collected many different large clinical studies, which we have found a distributed way of getting access to deal with legal issues. Health informatics, two partners are dealing with that to harmonize the data. Statistical risk and imputation models, and they then feed into hybrid models where we combine machine learning with multi-level mechanistic models, and this is my own expertise. Two partners deals with implementation issues, health economics and ethical implications. And finally, some clinical partners dealing with all stages of stroke. So from prevention to acute treatment at the surgery, and then rehabilitation and reintegration. So this is a sort of overview of all the roles and all the project partners. And just a little bit background to how we came up to this idea. And this is now my own 20-year journey, starting with modeling insulin signaling by iterating between experiments and model prediction 5 times. Just to characterize the insulin receptor, leading to how this leads to insulin signaling on the whole level, how this goes wrong in type 2 diabetes. And in all of this, we are very data-driven. So it's mechanistic models, but you see lots of data here on intracellular signaling, comparing lines, which are the simulations, and data, which are the dots. And this is for healthy controls in blue and for type 2 diabetes patients in red. And just keeping one of the intracellular responses, we move on to the organ level, where there are published models for all of the main organs in the human body, which leads to meal responses. This particular model that we use is approved by the FDA already. And this is in turn part of long-term models that describe weight change and disease progression. So moving to the specific disease progression of stroke, and in particular ischemic stroke, it starts with this type of altered metabolism, but then that together with high blood pressure drives atherosclerosis, which also is involved in inflammation. And then that together with heart failure and atrial fibrillation leads to an increased risk of thromboembolism and stroke. So looking at the different models describing these different aspects, I already showed you the beginning of the metabolism. Then we have liver fat and inflammation. Blood pressure models, again, comparing data with lines all the time. Simulations with data. Blood flow in aorta for short-term acute things. And then thrombosis, and finally up to the neuronal type of models, both pre-stroke and post-stroke. And how is this used in these different phases? Well, before, for motivation and prevention, you can have different risk factors that you discover. So for instance, liver fat, one of the early ones, is connected to obesity, diet, dyslipidemia, so you can do things about it. And it's a risk factor for instance, stroke. And then either before or after you have the stroke, so in the stroke, you are sort of want to do surveillance and treatment planning. But before and after, you want to do rehabilitation or prevention, so exercise. And by simulating different scenarios, we can show how these type of different risk factors are getting worse or better depending on what the person is doing, if he's eating or exercising and so on. And we do have a clinical protocol where you already do something similar, but just based on conversations. And this already lowers the risk of a cardiac event, including a stroke, by 30%. And we want to magnify this by bringing this technology into it. So here you see this type of simulation, again, comparing predictions with a line with the actual data of how liver fat is going down here in response to a 2-week change in diet. And then after this touch point in the clinic, the home monitoring, and then to these other phases, to the specialists and to the stroke surgery rehab and so on. So developing different softwares within the platform, but this is the one that I'm developing. Where you see here, you can choose the diet, LCHF diet here, low carbohydrate diet. This is an MRI image, and now behind the scenes here is a particular digital twin for a particular person. And here we happen to have an MRI image for him, but otherwise you will get the default one. You can rotate, you can zoom into different parts of the body. You can click on organs and get up what is inside the cells. You can get this type of microscopy images. And you saw these white droplets, they are the liver fat, the dangerous one. And here you see how this is reduced in response to the change in diet over 2 weeks. And if you want to get other ways, you can click again on the microscopy image to see how we believe that this would be reduced, so these white droplets have disappeared. So that's for diet. In a similar way, we have developed models for exercise, which is very similar to what you have shown, both using GAN and using this type of biomechanics models. And these are then connected to physiology. So you can look what happens in the blood, what happens in the different organs when you're exercising. And here we are also presenting this in sort of lecture performances where you actually can see yourself as a part of a performance using AR. So here you see me playing the piano, and this is a professional ballet dancer and the digital twin doing the same thing as her. Here, this is outside the Precise4Q, but since you're very much in this direction, we also do whiplash modeling where we do the same type of things. And here you see again comparison between data and simulations. For the hybrid modeling, there are a couple of things that we do. So you can show which risk factors are available, the ones you know, the ones you don't know. And for the ones you don't know, you can click on impute, and then you see that you have likely values for all of the non-measured variables. And then you can always click on risk as well. So you sort of get the current risk, and you can see how that is changing when you're doing this type of interventions. And for this, we developed a specific approach combining these mechanistic multi-level models with network models for the omics data into the machine learning model to calculate the risk. The other usage is for simulations, where we use these prospective cohort studies and these imputation strategies to start a model, and then the risk calculation to have simulations of how the risk is changing, and also how parameters and variables that we don't have in the mechanistic model, how they are likely to change as well in different outcomes. Yes. So summary and long-term vision of Precise4Q. It's to have a personalized, patient-centered, interconnected healthcare system. It starts already at birth, where you donate some cells, you donate some data. These cells allows you to do organs on a chip experiments on a little mini you, a physical copy of you, which you then can translate to the digital twin in the computer by scaling the different organs. Add new data and use this throughout the patient journey. So no matter where you touch point with the healthcare system or other things, build up these type of databases of digital twins that can be used for drug development, and even move outside of the typical healthcare situations to performances and gaming and so on, where you sort of can get this by osmosis. Just by living your life, you're learning about this, by seeing yourself part of a performance and learning how your bodies work. So this was my 9 minutes. Yeah, and this spin-off company. Yeah. So this was my 9 minutes for the Precise4Q.
Thank you very much. Now I would like to give the floor to Dr. Kirchner from Jülich Research Center to give a presentation on the EU Stands for PM project, a European standardization framework for data integration and data-driven in silico models for personalized medicine.
Okay, thank you very much. Do you see the full screen mode, everyone? Okay, excellent.
Yes.
Yeah, thanks. My name is Mark Kirchner. I'm the coordinator of EU Stands for PM, and today I will give you really a high-level overview of the project, what our goals are, where we're heading, and we'll also present you some of the results, some of the current results of EU Stands for PM. E stands for PM. We are a coordinating and support action under the Horizon 2020 program. The project runs for 3 years. We started in January 2019, and we have a consortium of 16 partners from 8 membership countries, and the project is coordinated by Forschungszentrum Jülich and by the project management agency Jülich. So these slides give you an overview of the underlying concept we are dealing with. What we want to know in EU Stands for PM is how do we get from data to knowledge through in silico modeling approaches, and in these in silico modeling approaches that are relevant for personalized medicine. And the data we're dealing with are basically summarized here. We call it big data in health. And the underlying question is, how do we get from the information we're having in these data and this big data have for health, how do we get there from data to knowledge? And more specifically, we want to use this knowledge to promote predictive in silico modeling approaches that have applicability in the clinical context in personalized medicine. And what we produce, or what we are aiming at, is to provide guidance for data harmonization and integration strategies for model validation, but also provide a proper legal and ethical frame. And we also provide data governance strategies. And currently, we are developing recommendations and guidelines in the context of in silico modeling approaches, specifically for data integration and model validation. And the target communities we are aiming at is European collaborative research, for instance, the project we heard about in the last half hour, funding organizations, but also regulatory bodies. This slide presents you an overview of the 4 central work packages of EU Stands for PM. We have work package 1 and 2 dealing with work package 1 dealing with different data sources that are the prerequisite for all modeling approaches that are dealt with in work package 2. Work package 3 provides a legal and ethical frame for the whole project, and work package 4 deals with the data governance pilot and awareness of the project. And the outputs are assessments, state-of-the-art analysis, reviews, recommendation, and dissemination activities. So I'm now present you some selected project outputs of EU Stands for PM, starting from the period when the project started until now. And I'm going along the different work packages, getting a little bit technical right now, but I hope I can provide you a more slightly specific overview of what we're working on at the moment. In work package 1, we basically produced a EU-wide mapping report currently dealing with data sources relevant for personalized medicine. And this is based on an online survey with 92 questions regarding the data sources and standards, modeling methods and modeling standards, but also data access and consent. Currently, we're preparing our our regular EU report, and also in parallel a manuscript that summarizes the results of this survey. Work package 2 that deals basically with the different modeling approaches. We produced a white paper that is currently an internal paper submitted to the European Commission only, but we are based on this based on the results of this white paper that features state-of-the-art modeling approaches and recommendations for data integration and model validation, but also collection of use cases. This white paper is a basis for a manuscript we're currently writing as a review article summarizing this on a higher level, and we hope that we will be ready for submission towards the end of the year. And this is led by the whole data in silico modeling approach is led by the University of Copenhagen. So, and the white paper is also the foundation for an ISO technical report, but I'm coming to this a little bit later. So, already published an article with the first set of guidelines in 2020 in the Journal of Integrative Bioinformatics. These guidelines are addressing different funding organizations, healthcare providers, journals, research group, and health providers, but also policymakers. If we look at the legal and ethical frame of the project, we published two reports, two reviews dealing with the legal and ethical considerations of in silico modeling approaches. And if you wish, you can download these two reports from the EU Stands for PM website. There is a compact version and a comprehensive full-length version available. I highly recommend this compact version that provides you within a few pages a very good overview of the challenges of legal and ethical considerations for in silico modeling approaches in personalized medicine. And there has also been a manuscript accepted, and it's currently published in a International Journal of Technology of Law and Practice. And this work is done and led also by the University of Copenhagen. If we look at data governance, we developed during the last year a so-called harmonized data access agreement that provides more flexible and easier access to controlled access data, basically those data that are deposited in several archives, such as the Genome-Phenome Archive. And this harmonized data access agreement provides specifically more flexibility to collaborative research project. It's fully GDPR compliable, and it's currently available for download as one of the default templates of the European Genome-Phenome Archive. And if you wish, you can get more information on the harmonized data access agreements on the EU Stands for PM website. In here again, we have a manuscript in preparation summarizing this whole process, and this part of the project is led by the University College of London. I mentioned this a couple of slides earlier. So we currently hold 2 liaisons with ISO technical working groups. The ISO technical working group 276 biotechnology and the technical working group 215 health informatics. And currently we are preparing an ISO technical report for the TC 276 called the requirements for in silico models for personalized personalized medicine guidelines for verifying and validating predictive computation modelings for EU collaborative research. This ISO technical report will be submitted in a couple of weeks to the ISO technical committee, and hopefully it will be accepted there and then will be provided as a specific ISO deliverable that will have a certain let's say binding force. In comparison, an ISO technical standard has a very high binding force, but there are also other ISO deliverables such as technical reports or technical specifications that vary in their binding force. So of course, we are coordinating and support action. We are networking project, and this summarizes you just a few projects we are collaborating with on certain levels. And here on this slide, I would like to present you our key players, basically the consortium. We have currently 5 ongoing Horizon 2020 projects as core partners, dealing with different computational models in relevant for personalized medicine, and they serve as in our data governance pilot with regard to the development of the harmonized data access agreement. We have key partners for standardization work, very prominent, the German Institute for Standardization called DIN, and which represents also the Mirror Secretariat for ISO in Germany. And we have several partners with highly experienced in data and model expertise, such as AXIA, Bayer, and University of Copenhagen, Rostock. The legal and ethical frame, I told you already, is provided by the University of Copenhagen, University of Oxford, and Linnaeus University. And we also have a regulatory body on board, the Federal Agency of Medicines and Health Products from Belgium. So, and I hope I could provide you a brief or an overview of the work of EU stands for PM. And with this slide, I will close my talk and thank the European Commission for funding EU stands for PM. Thank you very much.
Thank you, Dr. Kirchner, for your presentation. Now, next presentation concerns the backup project, risk stratification and personalized prediction models for back and neck pain, given by a colleague of Professor Hill, Professor van der Wind from Kiel University.
Okay, thanks very much, Ayana. I hope everyone can see my screen now. So the backup project is sort of like in the final stages of completion. Started in 2018 in 9 countries with about 13 partners. It concerns back pain, which I guess, like osteoarthritis, is a multidimensional health problem. And the aim of the backup project was also to make sure that we integrate information, sources, and data from those different areas of life that is affected by back and neck pain, including lifestyle, physiological and physical factors such as biomechanics, cell biology, glycans, but also psychosocial and social factors related to the workplace, for example. And the idea was similar to many of the other projects presented today, to integrate that data into models predicting the outcome of low back and neck pain when presented in primary care. So not so much about onset of back pain, because it starts often very, very early in life, even during children and teenage years. But once people are presenting with these pain problems, how can we best predict outcomes in terms of pain, function, and work? So this was a platform that now has several demonstrator apps, and some are more progressed than others, but they include a first contact app for GPs, physios, occupational physicians that first see a patient with back of neck pain. and I will mostly talk about that today. It includes a vocational advice app for patients who struggle at work, and they can use that as a self-management app. It includes economic models. It includes biomechanical prediction models, and an app that was developed earlier on as part of an EU project, looking at self-management related to physical activity, and that's the Self-Back app. That's now finalized and helps patients with mobile devices to increase their exercise, increase their physical activity, and all based on machine learning methods as well. So the backup first contact web app, which was developed very much in mind of making sure the model is used in everyday routine clinical practice. I think we all know that every year hundreds and hundreds of prediction models are being developed by universities across the world and by academic teams and companies, but very few are actually adopted in clinical practice and developed in a way that they help share decision making by patients and doctors. So that was a really important task for the backup first contact web app for patients with back and neck pain. It was all based on clinical research that was done at Kiel, where we developed a tool to stratify patients presenting with common pain presentations, and that includes neck, back pain, shoulder pain, knee pain, and multi-site pain, to risk stratify them into low, medium, and high risk based on presenting factors. That was developed into a tool that could be used in clinical practice. It was linked to specific stratified treatment options so that people at low risk would be offered treatment options that fit their risk profile around self-management, around reassurance, pain medication, whereas on the other end of the spectrum, people with high risks are offered much more extensive referral options, and that's all embedded in the GP systems. We then took that model that was being developed, but our prognostic modelers externally validated that in a different settings, externally validated it for other outcomes as well, function and work outcomes. And it was then taken to Multics, which is the data warehouse in Leeds we work with, to be integrated as part of the backup platform. The Research and Innovation Unit in the Netherlands has a lot of experience in terms of user testing e-health innovations. And we're at the stage now with this contact web app that it's being user tested across Europe in about 7 or 8 countries. It's been translated in 7 or 8 languages. And clinicians and patients are now actually testing it and using it to make sure that they understand the web app and how it works. So how is it embedded in the backup platform? It's the first contact for any patient, so it's completed by clinicians, occupational health physicians, and or patients. It is then integrated in a professional platform where ongoing data during the rehabilitation pathway for patients can be accessed. Patients can then use the data on the platform for their self-management, for monitoring of their symptoms, to offer data from questionnaires, from their accelerometers to show the clinicians how they're doing. So there's interaction between patients and clinicians on the platform. And then anonymized data is being extracted onto a research platform where in future researchers can request data, of course, with the right permissions and scrutiny in place to use it for their research questions. And we can use it to update the prediction models when more data will come in the future. So this first contact web app, as I said, is being offered to clinicians who first see a new patient with back and neck pain. They confirm eligibility of the patient and they complete a stratification tool. And I'll give you some screenshots later on. The stratification then visualizes risk, and it visualizes classification as low, medium, and high risk. And it then offers treatment options that are suitable for those different risk categories. and that have all been aligned with guidelines for the management of back and neck pain in primary care across Europe. It should be implementable across Europe and not only in a few countries. The app then generates a care plan as well that is shared with the patient so they can see what has been agreed and what the treatment choices are. So here are some screenshots. This is just one from the individual risk prediction, probably a bit similar as what we've seen before for predicting osteoarthritis. So on the left side is the risk stratification tool, which are 12 items that can be completed in a fairly short amount of time, considering that GPs only usually have about 7 or 8 minutes with their patients. It visualizes risk as low, medium, and high, but it also visualizes expected pain and function scores over time. And it highlights the need for vocational advice and supported work based on some items related to work. The patient is then offered, as I said, based on their risk, different treatment options that the GP or the physio can discuss with them, which might be around, for example, pain medication, might be around physical activity, might be around community resources for them to help with the back pain or physiotherapy. And the GP can click those options and offer self-management resources. There's lots of links to leaflets, patient exercise videos, and other local resources, which again are all adapted to the country in which we are working. And that generates, as I mentioned earlier, a care plan for the patient, personalized for them. It visualizes their scores again. It also highlights that if they, similar to the OA prediction model, if they reduce their weight or if they increase their activity, how much of their future pain scores might be reduced. And it for example, also gives them the date of their next appointment if that has been agreed by their clinician. And they can then enter, for example, pain scores over time, function scores over time, so they can monitor how their problem is developing over time. So very much all developed together with patients and developed with clinicians. It is still very much in development. At the moment, they're all demonstrator apps, but we hope in future projects to then test it and externally validate it across different settings. I mean, Jonathan wanted to share a few things that have come up and see where there are possibilities for collaboration or from learning from this project. And one, of course, is cross-validating prediction models across different institutes and organizations. So our model has been used in patients with knee and hip OA, so there might be opportunity for external validation of models between OActive and backup. What we have learned massively is that prediction models that have been developed in research settings might predict much better or less well compared to when prediction models are actually implemented at the point of care, because patients present information very differently at the point of care compared to when data are collected in a research setting. And it massively affects performance prediction models. So that is something I think we need to learn from these opportunities in risk prediction and opportunities in stratified and personalized care. And the other thing we have learned, and that's where our project has focused so much around that, is in order to make these models work in actually routine clinical practice, they need to be embedded in routine systems. Clinicians should not have to change their behavior so much, but they need to see benefits from tools like this. So adding shared decision-making tools and adding personalized care planning all within the platform is, we have found, the only way to make clinicians change their behavior and adopt platforms like this. Thanks very much.
For your presentation. Next presenter is Georgia Karanasiou from Fourth, that will present the InSilc project that is funded under the same funding scheme as OActive. The presentation is titled In Silico Trials for Advancing the Design and Development of Stents, Where We Stand, Challenges and Opportunities.
Can you hear me now?
Yes.
Okay, so thank you. I'm Georgia Karanasian from FORTH, Foundation of Research and Technology in Greece. FORTH is in fact the coordinator of InSilc project. I assume that you can see my screen, am I right? Okay,
Yes.
Great. So today I will present you, our presentation is entitled InSilc is in silico trials for advancing the design and development of stent, where we stand, challenges and future opportunities. So starting with the disease, coronary artery disease is caused by the growth of atherosclerotic plaques inside the coronary arteries. And it is in fact one of the leading causes of mortality in Europe and worldwide. And in order to treat the patients in which coronary artery disease and in turn atherosclerosis is present, we're currently using percutaneous coronary interventions with stents. So basically the first stents have been conceptualized in 1964. And since then we have different types and generation of stents. And the last generations were fully degradable stents. The first fully degradable stent was present in 2015, and it's a scaffold in which mainly we have the stent. It's inside the artery, it expands, so the artery is reopened. There is a drug in a coating that it is released, and the scaffold is able to completely dissolve after a certain period of time, that it is approximately 2 years. So currently, in order to test and ensure the safety and efficacy of such devices, these are initially tested in the laboratory in vitro, according to the ISO standards, in vivo on animals, and finally through different phases of clinical studies on humans. However, this whole pipeline has certain limitations in terms that the ISO mechanical testing is a slow and expensive process. The animal testing is idealized, and also the clinical testing is expensive, it's unpredictable. There are several ethical issues that are arising, and it's in fact the clinical, a main concern is that the clinical studies are based upon a one-size-fits-all approach. Whereas, for instance, the different types of atherosclerosis progress, the cardiovascular anatomy, and other comorbidities that the patient may have are not taken into consideration. So what we did in order to face this challenge is that we have created a consortium from different multidisciplinary partners. We have interventional cardiologists, technical partners with expertise in the field of computational modeling and simulation, experts in the field of in vitro mechanical testing and animal studies, biology experts. We have a company with experience in providing services for regulatory authorizations and clinical trials. And we have also experts in the design and development of cloud-based platforms. And we have also, we're very glad to have also with us one of the biggest stent industries worldwide, Boston Scientific. Apart from this, we're also supported outside the consortium from 3 additional stent companies. So the project InSilc aims to create an in silico trial platform for the design, development, and also assessment of fully degradable stents. And this is achieved by the integration of biological and biomedical knowledge, and also the utilization of advanced modeling approaches. There is an issue with my slides. Okay, so the platform, in fact, includes different models that are able to predict the performance of the scaffold in the acute short and also in the medium long term. And the models are on a cloud-based platform in which the different types of users, the stent industry, the interventional cardiologists, the researchers, and the contract research organization can have access through a web application. So our vision, in fact, is to supplement and accelerate the isomechanical testing, to extrapolate the animal testing results to patient anatomies, and also to supplement the clinical studies with virtual patients. In fact, we're moving towards refining, replacing, and partially reducing real patients through the integration of in parallel in silico trials. So here you can see the pipeline as suggested by Tina Morrison in 2019 for simulations in medical devices. And here, in fact, with orange is the pipeline of fully degradable stents before InSilc. So as you can see, only in bench tests is within InSilico studies are currently involved. But let's see how InSilc has been able to change this pipeline. So first, what we do is that we are using stents. So we design new stents, and we are using virtual devices, virtual stents, which are validated digital twins of the various designing solutions. Then we have a mechanical model that it is able to replace the bench tests that are now performed according to the ISO. And some of these tests are the dimensional verification, the force shortening, the dog boning, 3-point bending, and other tests. So the next pipeline is that we're able to, through the utilization of the 3D reconstruction tool, which is used for the creation of different arterial geometries, in which also the plaque components are included, and also through the employment of the plaque growth model, that it is a model that it's able to predict how the plaque evolves inside the arterial geometries. We're able to create patient anatomies and enrich virtual patients, creating patients with a diversity of morphological and clinical characteristics. So these 3D anatomies are used as input to the next module, that it is the deployment module. The deployment module can predict how the stent behaves, and which is the interaction between the stent component and the arterial tissue. And also we're able to correlate the results from the deployment module with the real clinical trials performance criteria, such as the risk of arterial wall or even stent damage. So the outputs of the deployment module are used as input to the myocardial perfusion module. So we're able to provide flow rate boundary conditions, and through the employment of the myocardial perfusion module, we're able to predict which is the myocardial perfusion under stress, and in fact, how myocardial perfusion is improved after the scaffold implantation. Now, following the previous models, we can also, based on the output of the deployment module, predict how the stent presence affects the local hemodynamics, and also have an indication of how the blood flow is inside the lumen, since the wall shear stress maps are possible additional clinical markers for in-stent restenosis. Now, as far as the drug is concerned, through the drug delivery model, we're able to predict how the drug is released to the wall and have indications in terms of time and space. And since the wall drug content is a possible additional clinical marker for suboptimal tissue healing and also for smooth muscle cell proliferation. Now, one of the final modules that we have is the degradation module that predicts how the stent degrades and how, in fact, this degradation affects the wall scaffolding. And finally, the last module is the restenosis module that can predict how the coronary wall responds at the cellular level to the stent deployment, and how, in fact, the local hemodynamics change during restenosis. So this is, in fact, the pipeline, and you can see what we can do is that we can change the animal trials, since we are able to reduce the animals used in current in existing animal trials. What we can also do is to refine the real clinical trials, since the 3D reconstruction and plaque characterization tool and also the virtual patients that we're able to create are employed through the different InSilico modules, and through the utilization of these virtual anatomies, we're able to predict results that we cannot predict so far through the real clinical trials. So here you can see the pipeline before InSilc, and here is the pipeline after InSilc integration. So InSilc can replace the bench test, can refine data in acute and short term, and can reduce and refine animal studies in real clinical trials. The next thing and step that we have done is that we have defined different scenarios of use, 5 different scenarios. We're able to compare existence, to compare different anatomic configurations and patient conditions, different clinical procedures, to design entirely new stents, or even to perform preclinical testing assessment. So I will go fast through to present you one scenario, scenario number 1. So we're able to compare 2 different fully degradable stents in a patient-specific anatomy, in which different types of arteries and plaque components are taken into account. You can see, for instance, that for those 2 different scaffolds in the same arteries, we have different levels of lumen gain, and we have also indications of whether there is malapposition or not. We're able to see which are the wall shear stresses, and for instance, for the first device, we can see that in the region of stenosis, we have increased wall shear stresses, and also that for the first device, from the degradation module, we have indication of increased stresses in the arterial wall. Now, as far as the validation strategy that we follow is concerned, we are following the VIN V40 ISO standard. Our validation is ending on next month. And all the module outputs are correlated with real clinical trials objective performance criteria. The data that we use are experimental for the in vitro validation, and retrospective and prospective data from 650 patients for the real patients clinical trials validation criteria. So as far as the business strategy is concerned, InSilc is a service-oriented in silico cloud platform. The pricing strategy that we will follow depends on the type of user, on the number of the patients that are employed in each in silico trial, and on the module that we will employ. But just to have an idea of the full pipeline, for the first scenario that we have shown, 10 days are required approximately. So finally, as far as the intended purpose of use is concerned, InSilc could be used as a decision support system for stent companies, or even as a training tool, or to be used for research purposes. And finally, InSilc could be also used as a supporting digital evidence for the regulatory evaluation of fully degradable stents. But in order this to be achieved, we should proceed with the formal validation based on the risk-informed credibility assessment framework, a formal reporting, and of course, consultations with the EU regulatory bodies and EMA. Thank you very much. This was from us.
Thank you, Georgia. Last but not least is the Carbon project, Marie Sklodowska-Curie training network, combining in silico, in vitro, and in vivo approaches to study cartilage and bone biology and engineering, presented by Professor Garis from University of Liège and KU Leuven.
Good morning, or lunchtime. Can you confirm that you see my slides on full screen?
Yes, sure.
Okay, thank you. So the aim of the Carbon project is it's slightly different from the ones presented. It's a training network. So the focus was also on the science, but also on the development of the ESR. So here you see an overview of the ESRs and some of the PIs in the project. So we wanted to train ESRs on early stage researchers on cartilage and bone biology, combining all of the work that has to do with cell culture, animal models, biomaterial development, bioreactors, to really raise the next generation of researchers with the skills to be able to make the advances that are required in this field. And there were 3 main research objectives, and I was looking at the role of secreted factors, extracellular matrix, and mechanical loading. That was one part. Develop new biologically inspired biomaterials. That was the second one. And then use this knowledge of cell biology and proteomics and mechano and pathobiology, integrated by computer modeling and simulation, to look at therapies. And rather, so in a nutshell, basically we were studying both ends of the hypertrophic switch between bone and cartilage. Some people going one way, other people going the other way. And rather than trying to give you within this 10 minutes or the 8.5 that are left, a complete overview of the whole project, I selected 2 projects that are not by any coincidence the ESRs that were working in my group, but where we can nicely show how the integration of all these different expertises and knowledges were working inside the project. So I don't need to explain osteoarthritis, but that was the goal. And one of them, we were working on 2 approaches to treatments. One was focusing on systems biology approaches for disease modifying drugs. The other one was looking at tissue engineering strategies for bone and cartilage. And so I will be presenting those now. The first one, looking at the diseases, was, as I said, taking a systems biology approach. So we start from the biological network, from the knowledge that we have. What you see here is a knowledge or a regulatory network that we assembled from the literature, but also with the help of all the ESRs that were working in this space, that were working on the mechano regulatory pathways, that were working on inflammatory pathways, coming from the logos that you see on the left. And this is now, this is soon going to be published as a network that can be consulted, where you can look at any of these nodes and then look at all of the data that goes in it. So this is also a kind of repository that we established for the whole project. Now, this then translated into a protein signaling network combined with a gene regulatory network, and that was the basis of our model. Now, of course, this is how we assembled it. We also took another approach where we went through the bioinformatics loop, assembling all the, in this case, microarray studies available, using a combat pipeline to get rid of the cross-platform batch effects, or of the platform-dependent batch effects, as you see here on the left, where when we do a PCA, where you see the different data sets nicely grouping per data set, and on the right-hand side, you see that with the pipeline, this has been taking off. And then we do an inference of the network that we're interested in, using different kind of approaches, which then leads to a final network that we can work with. Now, this network we then turn into a model by using an additive approach that has been previously published. And then you can use such a tool, and that's what it is, a tool to do 2 things. Looking at canalization, can our network recreate the chondrocyte, the articular chondrocyte or the growth plate chondrocyte that we're interested in? And then can we do perturbation analysis? And so when we do the canalization, so initializing, letting the model work, what we see is that indeed we end up with 2 stable states representing the hypertrophic or the disease state in case of OA, and then a SOX9 state, a healthy state of a chondrocyte. When we then investigate, for instance, possible combinations of all the factors that we have in our network that would lead to an arrest of the hypertrophy, when you do an in silico model, when you use the tool that I just showed, you can really do a lot of simulations and all different combinations and all different concentrations. When we do, we also did a validation in vitro using ATDC5 cells, and you see that it goes, the trend is very much the same. If you look at the yellow square, that's the starting point for both. Of course, doing this in vitro was taking way more time and resources, but the conclusions are the same. And I'm not going into the biological details, but you can see that this is an interesting tool to do a screening before you actually go into the experimental work. Now, this was one part. So one part of the platform focusing on really on OA, on drug treatments and on the different pathways. There was another part of the platform or of the Carbon project that was focusing more on tissue engineering, biomaterial development. And here we run a project that is very similar to some of the stuff done in OActive, where we used a multi-scale model of the whole environment as a starting point to design tissue engineering strategies or ATMPs. So starting from the knee joint, looking at the articular cartilage level, then going down to the cellular level in modeling the individual chondrocytes with their pericellular matrix, taking into account the different layers that we find in the cartilage and the different organization of the fibril orientation, using, again, partner information to come up with experimental data to feed this model. This was then, I'm skipping one here. This was then coupled with the intracellular regulatory network that I just explained in the first part to do these simulations to see how different loading of the knee resulted in different stimulation of the chondrocyte and a different result predicted by the intracellular network. Now, this will then ultimately have to fed back up to the higher levels, where if you then have knee joint problems, if you really have defects, you can look at the altered mechanics. And you can identify, based on this altered mechanics, you can then identify what the type of implants should be that would be able to withstand the forces that patients are exerting on their knee joint during the repair phase. And of course, this is modified by having different therapeutic or different physiotherapy regimes. Now, this is then input for work that is mainly done in Ireland, developing the biomaterials that would be used for 3D printing and the mechanostimulation of the cells that we put in there. So in a nutshell, what the project was able to do, I think we provided a very interdisciplinary training platform to the ESRs. And what was really great to see was that very naturally and very spontaneously, people started talking to each other, taking up bits and pieces of other people's work, integrating it in their own. And so there is a whole lot of unforced interdisciplinary and intergroup publications and work that is coming out of this grant. So I think we did good science. It recently ended our project, and there are some exploitable results in there for sure. And we will be, so results will be coming out for the coming years now that all the ESRs are wrapping up their PhD training and starting to look at the defense of their PhD. So if you want to see more results and the end report, it's available on the website, carbonresearch.eu. And well, I'd like to thank you for your attention, and I've managed to stay largely within time.
Thank you for your presentations. So now I would like to open the floor for questions using the chat box. My colleague Raquel Moreno will collect the questions and share it with the presenters. And I would like to give some more time for the last questions to arrive, and I will now share my screen. Just to give a short presentation about our upcoming conference. You can register. That will take place on April 23rd. And then you can join our discussions on how mechanistic computational models, simulations, and big data analytics can contribute to patient-specific osteoarthritis prediction and interventions. My colleague Elias will share more information on the chat room on this. just to give you an overview, during the conference, we will have several sessions and invited speakers from around Europe, including coordinators of similar EU-funded projects. So feel free to register and share the news with your network. For more information, of course, you can visit the OActive website. You can subscribe to our newsletter and follow us on our social media platforms. Back to the questions. Raquel, do we have any questions?
Hello, Joanna. We only had one question that was answered in the chat, and no more questions have come through.
Okay, thank you. So if we don't have any other questions, I want to thank you all for your presentations and for showing such an interest on our workshop. I should not forget to thank AXIA team for their support today during the meeting, and Ioana Baruni from CETRI for all the communications with the cluster projects. Following this workshop, we will share with you an evaluation form, as I mentioned before, in order to give us your feedback. And for sure, I would like to thank Mr. Tobias Wiesenthal for being today with us and all the presenters of this session. So before closing the workshop, I would like again to give the floor to the project coordinator, Professor Felekis, to say a few words. Kyriakos, the floor is yours.
Yes, I would like to thank you all for participating in this workshop, especially the speakers from the cluster projects, all the partners of the OActive consortium, and AXIA for the organization, as well as Ioana for bringing all these cluster projects together. Thank you very much, and I hope we'll see you in our conference in a month or so. Thank you very much.
Thank you.
Thank you. Have a nice day.
Thank you.
Bye, everyone.
Bye. Thank you
and a
for
nice
attending
weekend.
the meeting.
Bye.